What if I told you that metals, those shiny, solid barriers we rely on to block signals, are not as impenetrable as they seem? You shine a light on a sheet of copper, and sure, most of it reflects. What if I told you that metals, those shiny, solid barriers we rely on to block signals, are not as impenetrable as they seem? You shine a light on a sheet of copper, and sure, most of it reflects. Try sending a radio signal through steel, and it mostly bounces back or gets absorbed near the surface. That makes sense, right? Yet under certain conditions, electromagnetic waves go deeper. They find their way through tiny structures, sneak past expected limits, and behave in ways that classical physics never quite accounted for. This strange behavior is known as the Electromagnetic Skin Depth Paradox, and it's far more than a technical detail. It's a window into how light, energy, and materials interact in surprising ways. In this video, we're going to look at why high-frequency signals sometimes slip through metals that should block them completely. You'll see how surface electrons can carry light along a metal's edge, how tiny holes can transmit more light than large ones, and why shrinking things to the nanoscale changes the rules entirely. This isn't about rewriting physics. It's about understanding where simple models fall short. As we explore nanomaterials, quantum conductors, and new forms of communication and sensing, we're constantly reminded the world doesn't always follow the rules we learned in textbooks. Sometimes it writes its own.
How does electromagnetic radiation manage to penetrate into metals that are supposed to reflect or absorb it almost instantly? And why do certain waves go deeper, linger longer, or behave in ways that classical theory never predicted? Metals are famous for their shielding abilities. Shine light on a sheet of copper and most of it bounces off. Try to send a radio signal through a steel plate and it will be absorbed or reflected. Classical physics tells us that electromagnetic waves entering a conductor rapidly decay within a thin surface layer known as the skin depth. Inside this layer, the energy of the wave is absorbed and converted into heat by the motion of electrons, and beyond it, the wave practically disappears. So far, so good, until we look closer. The electromagnetic skin depth paradox arises when this tidy explanation begins to unravel under certain real-world conditions. In particular, when electromagnetic waves interact with nanoscale structures, high-frequency signals, or quantum materials, their behavior suddenly departs from classical expectations. What should be a neat exponential decay becomes messy, resonant, and sometimes even leaky. One striking example comes from Plasmonics, a field where light interacts with the surface electrons of metals at the nanoscale. In these systems, light doesn't just get blocked or absorbed. Instead, it excites surface electron waves, called surface plasmons, that ride along the boundary between metal and air. These waves can travel farther than expected, and under certain conditions, even pass through tiny holes in metal films more efficiently than large ones. That's a direct contradiction of the classical view that smaller holes should block more light, not less. At even smaller scales, the story gets stranger. In nanowires, thin films, and quantum conductors, the very notion of skin depth becomes blurred. As materials shrink, their internal electron dynamics change. Electrons bounce differently, scatter less predictably, and sometimes align into wave-like states that carry energy deeper into the material than anticipated. What should be opaque becomes slightly transparent. What should dissipate energy ends up guiding it. And then there's the issue of frequency. At very high frequencies, like terahertz or visible light, the way metals respond to incoming radiation shifts dramatically. The electrons can't respond fast enough to the oscillating electric field, and the metal becomes less reflective, more absorptive, or in some cases partially transmissive. The skin depth grows unexpectedly, allowing waves to infiltrate regions previously considered unreachable. Even classical engineering domains face this paradox. In complex circuits, proximity effects can cause electromagnetic energy to couple between conductors in unexpected ways. Fields intended to be confined to one path leak into another, defying neat predictions based solely on skin depth calculations. As we pack more components into smaller spaces, these surprises become design challenges. So what's really going on? The paradox lies not in the failure of physics, but in the limits of classical approximations. The idea of skin depth comes from simplified models, assuming ideal conductors, smooth surfaces, and bulk material properties. But nature's rarely that cooperative. At the nanoscale and in modern applications involving high-speed electronics, quantum computing, or bioelectronic sensors, we routinely enter regimes where those assumptions break down. It turns out that electromagnetic fields are far more nuanced than we thought. They don't just stop at the surface, they adapt, resonate, and sometimes find clever ways around the boundaries we impose. Fields can tunnel, leak, or hitch a ride on surface vibrations. Shielding, it turns out, is not always absolute. The electromagnetic skin depth paradox is a reminder that our intuition, trained on wires and metal boxes, isn't always ready for the subtle behaviors of light, matter, and electrons when pushed to their limits. It invites us to rethink how we define boundaries and to explore how energy moves, not just through space, but through structure, scale, and complexity. In doing so, it opens new frontiers for materials science, nanophotonics, and the invisible currents shaping our future technologies. The electromagnetic skin depth paradox reveals a surprising phenomenon. Electromagnetic radiation can penetrate into conductors, even those considered excellent at shielding, such as copper or silver. Classical intuition suggests that conductors should block electromagnetic waves completely, reflecting or absorbing them at the surface. However, in reality, the fields partially enter the conductor, decaying gradually with depth. This contradicts the simplistic view of perfect shielding and shows that metallic boundaries are not absolute barriers, especially at high frequencies. In high-frequency applications, the current in a conductor flows only within a very thin surface layer, well below a millimeter in many cases, despite the bulk material beneath, and it's like a raincoat that keeps most of the rain out, but a mist still seeps through the outer threads. Subtle, yet measurable. Skin depth refers to the depth below a conductor's surface where the electromagnetic field strength drops significantly. It represents the boundary layer where fields interact most with the material, losing energy, generating heat, and creating currents. This effect becomes more pronounced at higher frequencies where the field is confined to ever thinner layers near the surface. The skin depth is not constant, it depends on how rapidly the field oscillates, how freely charges move within the material, and how magnetically responsive the material is. A conductor carrying an audio frequency signal will see current distributed more evenly than one carrying a gigahertz signal where the current hugs the outer microns, much like sunlight penetrating water, bright near the surface, but fading as depth increases. The paradox arises because electromagnetic fields are dynamic, and even perfect conductors take time to respond to changing fields. The electric field induces a current, and the movement of that current in turn generates its own magnetic field. This interaction allows the wave to slip into the conductor slightly before it is dissipated as heat. Importantly, this is not a failure of shielding, but a fundamental property of how time-varying fields interact with materials that have both inertia and resistance at the microscopic scale. Devices using induction heating exploit this principle by generating intense fields that only penetrate shallowly into metals, creating heat precisely where needed. Much like pressing a sponge against a stream, the first layers get soaked quickly, but there's still a trace of moisture deeper in. Skin depth behavior is a classic example of emergent complexity from simple rules. Even when materials are uniform and equations are well-behaved, the interaction between waves and matter produces surprising effects. The system responds not with sharp cutoffs, but with gradual attenuation and frequency-dependent behavior. Small differences in composition or structure can lead to dramatic changes in how materials conduct or block electromagnetic waves. A multi-layer metal composite may reflect certain radar bands perfectly, yet allow others to partially enter, used in frequency-selective shielding technologies. Much like wearing sunglasses that block blue light but let infrared pass, where selective transparency emerges from internal structure. When electromagnetic waves penetrate a conductor, they deposit energy into the electrons near the surface. These electrons absorb the wave's energy and convert it into heat. This energy transfer is most intense near the surface, where the field is strongest, while the deeper layers see little to no energy. As a result, heating, signal degradation, or electromagnetic interference control is mostly determined by what happens within the skin layer, not the entire bulk. In microwave ovens or induction cooktops, only the surface of a metal pot interacts with the electromagnetic field. Yet this thin layer is enough to generate rapid heating. Much like cooking a pancake on a griddle, you only need to heat the contact surface, not the entire kitchen. From an informational point of view, the skin layer acts as a boundary interface, where electromagnetic waves encode data into matter. Sensors that rely on electromagnetic probing, such as terahertz imaging, magnetic resonance, or eddy current testing, gather information from just beneath the surface. The paradox is that these shallow layers hold a vast amount of useful information, especially in material science, quality inspection, and biomedical imaging. Skin depth limited signals can detect corrosion beneath a painted surface or analyze the blood content beneath human skin using optical methods. Much like reading the history of a tree, just from the first few rings, you don't need to cut down the whole trunk to learn its age. The skin depth influences the design of everything from antennae and shielding enclosures to photonic devices and plasmonic sensors. In advanced technologies, exploiting shallow field penetration enables ultra-thin circuits, field-enhancing structures, and even materials that can manipulate light on the nanoscale. As electronics scale down and frequency demands increase, understanding skin depth becomes crucial for thermal management, impedance matching, and surface engineering. Engineers use patterned nanoscale surfaces that manipulate the skin interaction to guide light in integrated photonic chips. Much like carving pathways in a riverbank to control where the water flows. Even though it touches only the edge, the direction is fully shaped by the surface. Although skin depth is mathematically defined, real-world behavior can deviate due to imperfections, grain boundaries, surface roughness, or nonlinear effects. Additionally, at very high frequencies or in nanostructures, quantum effects and surface plasmon resonance can further alter how fields interact with electrons. Designing effective shielding or signal pathways requires deep knowledge of materials, frequencies, and geometric constraints. Engineers designing 5G antennas must optimize conductor geometries that minimize skin loss while maintaining mechanical integrity, a difficult balance, much like designing armor that is both thin and unbreakable, where the weakness is not the material, but how deep the enemy's blade can reach. Skin depth behavior is a frontier for nanophotonics, quantum plasmonics, and adaptive shielding. As our understanding of surface field interaction grows, engineers are developing materials that manipulated electromagnetic skin layers, such as cloaking devices, field amplifiers, and invisible circuits. In the future, energy, information, and function may all flow along engineered surfaces rather than through the volume of materials. Research into ultra-thin conductive coatings aims to make wearable electronics nearly weightless and invisible, relying entirely on the skin layer for performance. Much like writing a symphony on the surface of a drum, the music exists in the skin, not in the silence within.